Guys, this is dark and it has a huge mass, and it's small. That's 3 smoking guns right there implicating a supermassive black hole. Space can be scary, and thinking about the dangers that lurk within the vast expanse of space can be terrifying. While this applies to the entire concept of space exploration, one part that has always been intriguing and terrifying at the same time is black holes. These beasts of power have been the subject of countless research studies all across the globe. Scientists have been trying to figure out just what black holes really are and what lies within them. But all of that changes now. Neil deGrasse Tyson just revealed something huge. Our black hole is less massive than the one in the center of the Andromeda Galaxy, our nearest big galaxy. So, we have black hole envy, and I think we do. We finally see what's inside a black hole, and, well, all of it might just blow your mind. Created from a massive explosion, a black hole's mass is concentrated in an incredibly small region, creating a gravitational force so intense that nothing, not even light, can escape from it. Once something is in there, it's going to stay there forever. These forces of energy come in various sizes, ranging from stellar black holes, which can be a few times the mass of the Sun, to supermassive ones that exist at the centers of galaxies, with millions or even billions of times the mass of our Sun. Scientists have observed the effects of black holes indirectly for decades. Every new piece of data uncovers more secret. Even though they seem so massive and powerful that they can't possibly have an origin story, they do. Black holes don't just exist in space, they're created. They need the remnants of massive stars that have exhausted their nuclear fuel to be born. These stars undergo a supernova explosion, a spectacular event marking the end of their lives. During a supernova, the outer layers of the star are violently expelled into space, while the core undergoes gravitational collapse. If the core's mass is several times larger than that of our Sun, the force of gravity overwhelms all other forces, causing the core to collapse inward. This collapse compresses the mass into an incredibly small volume, creating an object with a gravitational field so powerful that nothing can escape its grasp, thus creating a black hole. The size of a black hole is determined by its mass. Stellar black holes, the most commonly known type, have a mass range from a few times to several tens of times that of our Sun. At the core of a black hole lies the singularity, a region of infinite density and space-time curvature. According to our current understanding of physics, the laws of nature break down at this point, and conventional theories cannot fully explain what happens within the singularity. In physics, a singularity refers to a point in spacetime where certain quantities become infinite or undefined. Singularities appear in theoretical contexts like at the beginning of an expanding universe, the Big Bang singularity, and within black holes. As we study the Big Bang singularity, a fundamental challenge arises. General relativity, which governs gravity's behavior, breaks down as we approach this initial state. A new theory combining general relativity with quantum mechanics is needed to resolve this issue. Black holes contain singularities at their cores, where the gravitational pull becomes infinitely strong. Matter and energy that fall into a black hole reach the singularity and become infinitely compressed. This concept goes beyond our current understanding of physics. The challenge of singularities has led scientists to seek a theory of quantum gravity, which aims to unify general relativity and quantum mechanics, offering insights into singularities and the universe's workings. One approach to addressing singularities is loop quantum gravity. This theory suggests that at extremely small scales, spacetime is quantized, meaning it consists of discrete, indivisible units. These units are interconnected loops or spin networks. According to this theory, the discrete nature of spacetime prevents infinite densities and curvatures that create singularities in classical general relativity. As matter collapses toward the core of a black hole, spacetime becomes increasingly tiny, preventing the matter from reaching an infinitely dense singularity. Instead, the collapsing matter encounters a quantum bounce near the core, where it rebounds and begins to expand. This leads to the formation of a new spacetime region inside the black hole, sometimes referred to as a quantum black hole. Stellar black holes, the most commonly observed type, form through gravitational collapse at the end of a massive star's life. Once a star exhausts its nuclear fuel, the outward pressure generated by nuclear reactions no longer counters gravity, causing the star to collapse under its own weight and form a stellar black hole. Despite their mass, stellar black holes have incredibly small sizes, just a few kilometers in diameter, making them remarkably dense. The immense density of a stellar black hole leads to the formation of an event horizon, a boundary beyond which nothing can escape. This event horizon marks the point of no return, where the gravitational pull is so strong that any object or information crossing it is trapped forever. Intermediate mass black holes have masses ranging from thousands to tens of thousands of times that of the Sun, influencing their surroundings and galactic evolution. Supermassive black holes, often found at the center of galaxies, remain an area of active research. One hypothesis suggests they evolve from smaller black holes through accretion, where matter accumulates around a black hole, merging over time to form a supermassive object. Charged black holes, such as Reissner-Nordstrom and Kerr black holes, represent unique variations. Reissner-Nordstrom black holes are charged but non-rotating, while Kerr black holes are both charged and rotating, introducing unique phenomena like frame dragging. These types are mostly theoretical, as most black holes are neutral, lacking a net electric charge. With technology advancing, scientists have observed black holes directly. In April 2019, the Event Horizon Telescope captured the first image of a supermassive black hole in galaxy M87, located 55 million light-years from Earth. Additionally, gravitational wave observatories like LIGO and Virgo detected ripples caused by black hole collisions, marking monumental breakthroughs in confirming their existence. Though we're still trying to fully understand black holes, they are a reality. Continuing to study them is crucial for understanding the universe's nature and behavior. Intermediate mass black holes, while the precise mass range is still an area of ongoing research, are generally thought to have masses ranging from thousands to tens of thousands of times that of the Sun. These colossal entities occupy the central regions of most galaxies, including our own Milky Way. Their significant gravitational influence plays a crucial role in shaping their galactic surroundings and impacts the evolution of galaxies. The formation of supermassive black holes remains one of the biggest mysteries in astrophysics and is still not fully understood. However, several theories have been proposed to explain their origins. One prominent hypothesis suggests that supermassive black holes evolve from smaller black holes through a process called accretion. In this scenario, as matter, such as gas, dust, and stars, accumulates around a black hole, it forms a swirling disk known as an accretion disk. The immense gravitational pull of the black hole draws this material inward, causing it to spiral into the black hole and merge with it. Over vast periods of time, this continuous accretion of matter allows the black hole to grow to a supermassive scale. During the accretion process, enormous amounts of gravitational potential energy are released as the matter falls into the black hole. This release of energy powers some of the brightest and most powerful phenomena in the universe, including quasars and other active galactic nuclei. Away from these supermassive black holes are charged black holes, which represent a fascinating variation in black hole theory. Charged black holes are characterized by the presence of an electric charge. There are two main types of charged black holes: Reissner-Nordstrom black holes and Kerr black holes. Each type exhibits distinct properties based on the relationship between the black hole's charge and other factors such as rotation. Reissner-Nordstrom black holes are charged but non-rotating, described by the Reissner-Nordstrom solution in general relativity. The charge of these black holes affects their gravitational field. Although structurally they are similar to uncharged black holes, they possess an event horizon, and the size of the event horizon depends on both the black hole's mass and its electric charge. On the other hand, Kerr black holes are both charged and rotating, introducing unique phenomena such as frame dragging, where the rotating black hole twists the surrounding spacetime. These black holes have both an outer horizon and an inner region called the Cauchy horizon, a boundary separating the exterior from the singularity within. The presence of an electric charge in a black hole introduces a repulsive electrostatic force in addition to gravity, affecting the behavior of nearby particles and matter. Charged particles, for instance, may be repelled by the black hole's electric charge, altering their trajectories. While charged black holes are theoretically possible, they are not widely expected to exist in nature. Most black holes are thought to form from astrophysical processes that result in neutral objects, meaning they lack a net electric charge. If a black hole were to acquire an electric charge, it would likely neutralize itself over time by attracting opposite charges from its surroundings. We've learned a lot about black holes over the years, but actually seeing one changes everything we know about these enigmatic entities. With technology advancing rapidly, scientists have been able to observe and confirm the existence of black holes. Not just one, but two groundbreaking observations have provided direct evidence of black holes. The first direct observation occurred in April 2019, when the Event Horizon Telescope collaboration captured an image of the supermassive black hole at the center of the galaxy M87, located approximately 55 million light-years from Earth. The image showed a glowing ring of hot gas surrounding a dark central region, representing the event horizon of the black hole. This observation confirmed the existence of supermassive black holes and provided unprecedented visual evidence of a black hole's event horizon and surrounding accretion disk. Then gravitational wave observatories like LIGO and Virgo made additional observations. They detected ripples in spacetime caused by the collision and merger of black holes. The detection of gravitational waves in 2015 was a monumental breakthrough in astronomy, providing indirect evidence of black holes and confirming the existence of binary black hole systems, where two black holes orbit each other before merging and producing powerful gravitational wave signals. Black holes have long captivated the imagination of both scientists and the public, inspiring numerous theories and speculations about their nature and role in the universe. Recent advancements in observational technology have enabled researchers to explore black holes more deeply than ever before. For example, the detection of gravitational waves from merging black holes has opened a new avenue in astrophysics, allowing scientists to study these elusive objects through the ripples they create in spacetime. The study of black holes also intersects with fundamental questions about the fabric of the universe itself. One major area of research is the potential connection between black holes and dark matter. Dark matter, which makes up a significant portion of the universe's mass, remains largely mysterious. Some theories propose that primordial black holes, small black holes formed soon after the Big Bang, could account for some of this elusive dark matter. Furthermore, the concept of black hole thermodynamics has emerged as a fascinating field of inquiry. According to this framework, black holes have entropy and temperature, suggesting that they obey the laws of thermodynamics. The famous physicist Stephen Hawking introduced the idea that black holes can emit radiation, known as Hawking radiation, due to quantum effects near the event horizon. This radiation implies that black holes are not completely black and can eventually evaporate over astronomical time scales, leading to intriguing implications about the ultimate fate of black holes and the information paradox. The information paradox itself raises profound questions about the nature of information in physics. When matter falls into a black hole, it appears to be lost forever, contradicting the principle that information cannot be destroyed. This paradox has prompted debates among physicists, with various theories proposed to resolve the dilemma, including ideas suggesting that information may be preserved in the radiation emitted by the black hole. In addition to their scientific importance, black holes have captured popular culture's imagination, appearing in countless films, books, and art. Their portrayal often leans toward the dramatic and mysterious, reflecting humanity's fascination with the unknown. Black holes serve as a powerful metaphor for incomprehensible forces and the limits of human understanding, challenging our perception of reality. Researchers continue to explore the environments surrounding black holes.